So what is a model? The model is a term that you're going to hear all the time when you're talking about machine learning. It's probably really overused and probably very badly explained in general. So I wanted to give a clear explanation of what is a model, one of the central concepts in machine learning. A model is as simple as this. It's a mathematical function which takes in some features of an example and makes a prediction. And that could take all kind of forms, but the model is just a mathematical function. It might be something as simple as this. We've got some example which I want to make a prediction for, and I've got the prediction which I make, and then there's the form of this model, which in this case is very simple, but it could be much more complicated. And this isn't even as complicated as they get, and that's actually only a part of that model. But back to it, the key thing to note is that a model is just a mathematical function which is going to make predictions. It could be that it takes in an image and makes predictions which are the classification of that image. It could be that it takes in a row of data from a database and it predicts a house price as a single number. It could be that it takes in an audio waveform and outputs a different waveform in a different language. The model is the part of the system which takes in the input and turns it into the output that you want. And really you can frame pretty much any problem in this way where you have an input that you want to map to an output. And if you can do that, you can solve so many different kind of tasks, like some of the ones I mentioned. It might be computer vision tasks, natural language processing tasks. It might be predicting whatever you want, really. That's the point of the model. Takes in features, outputs a prediction. So think about a model globe. A globe, it looks something like the Earth, but obviously it's in much less detail. It's not an exact representation of how the Earth looks or how it behaves or what it's doing right now, but it is useful. Useful for a number of reasons, because it can show you where countries are and such. And if you had a better model, it will be more accurate. So you could start drawing kind of the roads on the globe, you could start drawing more and more details, and there's some spectrum between a very simplified globe and the real world. The more complicated you can make that model globe, the better idea you can see and understand what's going on in the real world. And obviously, if you had a perfect model, which was an exact copy of the real world, you'd be able to make any prediction about the world and know the answer. You'd be able to say, where is Harry at any point? Well, I can just look on the globe. But of course, building those extremely accurate, well, exactly accurate models is often impossible, or at least impractical. Only in a few very rare cases can we actually get to a true understanding of the underlying dynamics of a problem and have a perfect model. Almost always, we're making an approximation for how we think something behaves based on all the experimentation we've done. Even some of the most widely used and basic equations in physics that you might have heard of, they're models of how the world works, probably not exact. But all of them can be represented as mathematical functions which take in some inputs and produce some outputs. And there's basically an infinite number of ways that you could write an equation to map from those inputs to outputs, which basically just gives you the idea that there's so many different ways that you can model things. So you're probably going to get into the details of how some of the most popular and useful models are represented.